Stanford University.
Yushen Chen. I work in Zynga. Today I would like to talk about some of the data access needs we're trying to solve to get analytics data available to our applications. We use a system called Membase. I don't hear that mentioned in some of the talks, so I want to describe that a little bit today. And so we have a Vertica data warehouse from these guys from Vertica, and most of our tracking data from game web servers will reach the Vertica data warehouse. And we'll actually do some computation to calculate aggregates about user. And these aggregates will be fed into Membases in a form to be consumed by web server code. I'm going to talk about a little bit about Membase and how we're deploying it in our data centers, and then what's the content of data in here and how we access it, and then some operational, how we run it in operation, and some of the challenging next steps. So Membase is basically the key value store like Memcached. It's the same protocol. What's additional is it offers persistence and replication. It's developed by a company called Couchbase with contribution from Zynga. With replication, we use that a lot to support Zynga's deployment. We deploy it in one master cluster and several slave clusters. This module I'm talking about, Zynga Data Services, one of the bigger deployment of Membases inside Zynga. Writes only reach the master cluster, and replication takes care of propagating the writes to the slaves. So what kind of data do we have? We have about 5 billion items. And these, some part of the aggregates I mentioned earlier, and some are the data actually are not aggregates. The games can access that storage in it's writable to the game as well. They actually use that to communicate certain interesting data across different games, and we use that in a host of our services. So the two types of data are here, daily aggregates, and then also information on each user. For example, we want to detect a user made a purchase in one game, in another game, and that might trigger certain actions in this other game. So that's how we use this Membase to communicate that. We have two types of access. It's a direct library plus a subset of users or games use REST to access that. It's used by most of the Zynga games, as well as a lot of services that Zynga use internally. We use that to filter and quantify users, and we also use that to compare users and sometimes matching users. So we have a lot of different use cases that we're going to try to integrate into our API. So operation-wise, we use Zookeeper to configure the cluster, and MCMax, which is a connection pooling layer on top of that to manage connection caching. And we also use Moon and Nodules for alerting if the systems are not running fine. One of the things we need to watch out for, which is one of the part that Membase still needs to improve, is the replication. We have different data centers. We want to make sure the data are in sync, so we need to alert whether they're out of sync. And we have checks in that to monitor if replication's happening successfully. And one of the things, like I mentioned, Membase offers persistence. So we use that to do backups. Not all our data can be pushed out easily and quickly. So we want to be able to recover from local disk, which is a lot easier than if we have to ask either games or central services, in this case from Vertica, to publish the data again. And lastly, some of the next steps, like I said, replication is very important for us because we have different games in different data centers. and we want to improve the performance of replication. And some of the problems we're seeing, if we have too many items being changed quickly and the queue will build up, at this time the replication might fail. And I also want to explore server-side clustering. It's a plus and minus, and we want to make sure that works well and better performance. Thank you.
Okay, this is my attempt to help Jacek out. So benchmarks are a great idea. It gives a level playing field and encourages vendors to have features that make your benchmark go fast. And basically, Jacek would like to see commercial systems do a lot better on LSST's workload. So this benchmark is an abstraction of LSST, which is an astronomy workload. Basically captures the essence of a whole bunch of other fields in addition to astronomy. So I think it's fairly general. Jacek's workload looks like this. Telescope takes this. Then what happens is that you end up doing a whole bunch of workflow downstream. So you want to capture the end-to-end processing from telescope to derived data products to queries. So basically, this benchmark is ingest a bunch of raw data, cook it into a bunch of derived data products. What that means is look for stars in these images, store the stars as observations and other kinds of celestial objects. And then if you point this telescope to the same place in the sky at some subsequent time, you'll see the same observation again. Couple those observations into trajectories. And then the benchmark has queries on the raw data, queries on the observations, queries on the trajectories. And some of them get pretty hard. There's a lot of spatial queries. There's a lot of basically raster-like processing. Jim Gray had a paper a whole bunch of years ago, which was 20 popular Sloan Sky Survey queries. This was all on the Cook-derived data, so the big difference here is that this is the end-to-end problem as opposed to just queries to the Cook data. So I already said it's a bunch of raw imagery. It's a terabyte of raw imagery cooked into observations, as I just said. Basically, this is a clustering algorithm, and it gives you polygonal spatial data. It's further cooked into trajectories. Trajectories are cylinder-like things that move over time. And it's store all of this stuff and run queries on it. So in the essence of TPC, the regular is a terabyte. It scales up and down to get harder and easier. And there's a whole bunch of parameters, which is like how big an area of the sky do your queries look at. So you can make the parameters make this benchmark much easier or much harder. And so load some data, cook what you loaded, and then run a collection of queries that are on raw data and cooked data. So that's basically the benchmark. The details of the queries are on the poster outside that you can go look at during the break. And what we did was we've run this benchmark. We ran it on MySQL, 10 nodes worth of MySQL with Facebook-style application-level sharding, which was a huge pain in the butt. And on SciDB, SciDB does the sharding automatically. SciDB is about a factor of 15 faster than MySQL on this benchmark. It's faster for a variety of reasons that are all reasonably significant. The first one is First one is you've got to have reasonable spatial database support. because there's a lot of polygonal data. And MySQL spatial indexes aren't that good. Part of the benchmark is load. And MySQL is not very good at loading. And that's one thing that users routinely complain about. The other thing is that there's a whole bunch of attribute data. And if you store it column-wise, it tends to be faster than if you store it row-wise. MySQL stores it row-wise. SciDB stores it column-wise. SciDB gets a lot better parallelism, because if you're taking an image and you want to pick out the observations, you want to have a chunking system. Thank you very much.
I'm Maya Gokhale, and I'm going to tell you, the title says it all, Compute-Capable SSD Architecture for Next-Generation Non-Volatile Memories. Arup Dey is the student who's been doing this work for his PhD under the direction of his advisors, Rajesh and Stephen, and I'm his mentor at Lawrence Livermore. So the crux of this work should be very resonant to the audience here from what I've been seeing today, because what we want to do is bring the query to the data in the penultimate form. So we're not actually moving it to the bits of storage on the flash or the PCM, but we're bringing it to the storage controller. And the work is really motivated by the observation that in future storage architectures, that with a DRAM latency of 1, disk is out here at hundreds of thousands in latency. However, PCM, all varieties of the new non-volatile memories that are emerging slowly, but emerging, certainly flash is here, offer much lower latency that's more memory-like. In this work, we are looking at these non-volatile memories being connected to the I/O controller rather than to the memory controller, and as such, there's an I/O bottleneck. So what we'd like to do is to move the queries, the computation, as close as we can to the data and within the storage controller. This is the architecture that we're prototyping. It's built around the B3, which some of you may know is a 4 FPGA prototype with 64 gigabytes of DRAM. So we're emulating the storage controller and the PCM or flash or whatever memory we would have. And I think the contribution of this architecture is a method for separating the memory controller, which is talking to the non-volatile memory, from the storage processor, which is actually going to be doing the compute algorithms. In this particular incarnation, there's 4 FPGAs, and therefore you see 4 groups of storage controller and memory controller in a ring on the PCIe bus. To go a little bit deeper, the storage processor has a request manager. It has a DMA engine to talk to the memory controller. And in this example, this is a grep kernel. So an obvious application might be filtering, looking for certain patterns, such as DNA substrings within the data blocks themselves. So that's a representative kernel that would be run as a stream processor. So it would get the bytes off of the non-volatile memory, do the filtering, and then return results over the I/O bus back to the server. So this is the architecture within the FPGA of the storage controller. And what we've done is actually put the compute kernel in hardware. So the sorts of applications we're looking at are filtering, obviously, various sorts of filtering applications. Range queries might work in that also, where you're looking at scientific data and you want to pull records whose fields match certain range criteria. But we're also looking at less obvious applications, such as doing graph processing, graph traversals within the storage controller, talking directly to the flash or PCM memories.
Okay, thank you.
Hello, everybody. My name is Nikolai Malisky, and today I present the proposal of next EPIX data storage. So the few words about the EPIX. This is a control system used in many accelerator projects in the world. United States, for example, is just used in the majority of the national labs in the SLAC, Berkeley, Los Alamos, Argonne, and Oak Ridge. And the next slide that presented an SLS2 built in the Brookhaven National Laboratory. So in the short, accelerator project is a big enterprise involving the many different the system and also encompass of the various heterogeneous physical devices. So the new project coming with the new challenges, and eventually we're coming up to the new scale, like 1 million of streams of time series that we need to collect in the database and archive. So for the post-processing, the analyzing, troubleshooting, and also for commissioning of the operation. Rephrasing the statement of the previous, of the yesterday, so certainly relational database is a scale, but don't scale very well, okay? So we really need new technologies to solve this problem. So Apex likes challenges, and so looking also around for the new application. This one is an example of a beamline data acquisition system that coming together with the accelerator projects. So again, new projects coming with the new technologies, and you can see like detected data rate of for the new facilities on the scale of the 50 gigabyte per second. This is a really enormous rate. So this data, of course, is a process of online in runtime environment, and also with the usually tomographic application is just coming with the 3D imaging that we need to store in the file system. So we're working with the scientists, and we have some progress. It's hard. So eventually we're coming with a common data format that's going to use for the different experiment. So, but again, so this is a very similar problem that Ralph presented yesterday, so that we need some common service to work with multiple files. In addition to that, these files also correlated with the control data, because experiment is quite difficult, and certainly the settings is really important, and they correlated with the scientific data. So again, so we need some common solution. So that after the analysis of several technologies, eventually that I found that, and pleased to find that this is a very natural solution suggested by the XLDB the team. They call array-oriented the conceptual model. So frankly, I'm looking for the some approach for the several years. From my perspective, it's a really natural step in the evolution of column-oriented databases. So in addition to the natural representation of the previous use cases, this XLDB project coming with a very efficient interface, integrated very important features like column-oriented approach, chunk-based approach, and many others. So that after the sourcing, after analyzing the source code and the several different benchmarking and the prototyping, our system eventually came with some proposal of integrated system. Okay, so that it presented 2 weeks ago at the Apex collaboration meeting in the Switzerland, and very good accepted. In short, using that, again, so the Miguel term in the in situ database approach, we expect to use the XLDB as a common platform to connect all different subsystems in our environment. Actually, so to bind together the past, present, and future. So from the different perspective, it's also very interesting. So because we consider XLDB will be another service. Okay, the first of all is especially important for the beamline experiment. It'll provide additional service doesn't conflict with the existing toolkits that using the XLDB. For the HDF5, but also you know that it's also related to the today's discussion. So this is really the hybrid solution, the hybrid environment, combining to the databases and the file system. So we expect, so we need to really run that quite complex data mining procedures as well, in addition to XLDB using the different technologies. Thank you.
I'm Siva from EMC Greenplum. So this whole extremely large data thing is getting quite popular, I believe. And so what's happening is, if you have a large amount of data and it's getting popular, a lot of people want to ask questions. That leads to a problem for a database management system. So yeah, this is a problem when you get really popular. And you want to manage this. A database management system has to, well, manage this problem. So what is the problem? There is finite amount of resources in a database management system, which is CPU, memory, I/O, network, and maybe some others. And there's a lot of concurrent activity. Like I said, many people want to gain insights into this large amount of data, and they all want to ask these questions now. And management system must be able to support this. The problem is, not all questions are equal. Some of them are more important than others, and this depends on time of the day, time of the month, whatever. So this, for example, these could be loads, these could be weekly reports that you ask, and these could be more exploratory analytic queries, which take a really long time, and this is something that you've never asked before. And each of these, like I said, could have different business value at different point in time. Now, the impact on a system may be orthogonal to the business value. It could be a really simple query from a technical perspective, but it's really, really critical from a business perspective, and vice versa. So the problem here is, how can a database administrator keep everybody happy? How does he align resource usage with the business value of queries? So the solution that we came up with in the Greenplum parallel database is fairly straightforward, which is, upon arrival, we determine what is the business value of the query. And that typically involves more than looking at just the SQL text. It involves a whole bunch of contextual information. But once you do that, we translate that to what is the fair share for this query, what is the fair share that it should get of CPU and memory and other resources. And once this is determined, we try to reserve these resources in a certain sense. And if these resources are available, then the query can proceed towards execution. And the second part of this is, once you've determined the fair share, you need to ensure that the query behaves. It behaves per the allocation. And that's the runtime resource allocation part. And adjust behavior as necessary. So given this, there is a slight difference between CPU and memory, as many of you might have noticed. CPU is like a bottle of Coke. Let's say you have 8 party guests who've come over, and you have poured out 8 glasses, and a 9th one arrives. You can redistribute it without too much trouble. Memory is like a pre-sliced pizza. If you get a 9th guest, it gets a little awkward trying to, and this analogy is making me hungry. Okay, so CPU sharing. How we handle CPU sharing is, let's assume that we've calculated the fair share through some means. I mean, that's a well-researched topic. But what happens during execution is, a query gets translated to a query plan, which is like a tree of operators, each of which does something special. And each query operator continuously measures itself. It sees how much of CPU it's been using. And it compares that against what is its fair share. And if it uses too much, it just sleeps a little. It gives it up. So that way, it dials down its usage. And rinse and repeat. This process occurs at extremely high frequency, so we're able to meet any target for CPU usage. And I/O and network bandwidths are very similar to this in nature, because you can give it up by just not doing anything. Memory, on the other hand, is, like I said, a little trickier, because once you give it up, it's very difficult to reclaim it back. So we took a slightly different approach, in which case, in this case, every query operator in this plan gets a portion of the memory that we reserved for the entire query. And this is determined using a memory distribution algorithm. Oops. OK. And data's too large, they spill. And thank you. All right. Great.
Hi, I'm Robert Reed, Whamcloud. Here to talk about Lustre. Never felt so much like the ugly duckling before. So let's get going. So Lustre is a file system, of course. It's GPL. There's a large community behind it now that didn't used to be. And it's still the industry-leading HPC file system. HPC, yes. It's got some good hero numbers. Actually, I have a nice picture of the Oak Ridge cluster. We'll talk about it in a minute. Good scaling. It works well in both a LAN and WAN environment. It's a general-purpose file system that works at high scale. So this is the Oak Ridge cluster. Scott was talking about a bit of this later. This is a piece of it anyway. This is just Jaguar and the other bits. So Jaguar is a big petaflop, big flop supercomputer. Spider here, this is the Lustre file system. It's, like 6 petabytes or so. And it's being used not just by one compute resource, but all of these other resources as well. So it's a shared resource. There's multiple applications running on here and different things happening over there, which explains also why they don't really see the hero number all the time, because it's being chopped up into a bunch of different pieces. So it's a POSIX-oriented basic file system. It's coherent, it supports data, metadata caching, has a DLM to support the caching. But the interesting thing about Lustre is that although there's a metadata server to support the POSIX namespace, the data is stored on distributed objects. And there's some interesting things that can be done there. The downside of Lustre is POSIX is basically a 70s I/O model. The big innovation on top of tape that you get with a file is random access. And we'd really rather you didn't do random access because it really slows things down. The concurrency isn't great, and it just doesn't, and concurrency is a problem. It's not so big a deal. I mean, the single disk, when your concurrency model is based around a spindle, then the POSIX file system, it's been working all right for us so far. But when you get an SSD that really demands a much higher amount of concurrency on a per disk, or per device rather, level, POSIX isn't going to do it for us. In addition to that, and this was mentioned earlier, that the POSIX namespace works well at human scale. It doesn't work well when you're creating billions of objects, and using the name as metadata is the wrong thing to do. So we need a better interface in between the parallel storage and the parallel applications. So what we're proposing to do with Lustre is to create distributed application object storage, or DAOs for short. And this is just drawing a blank. It is object, so like I said, Lustre is object storage underneath. So this is creating a system call interface essentially to this distributed object storage. So probably would see middleware using this to manage schemas for individual applications. And the way this works within Lustre is you still have a namespace that's used for legacy applications, and the DAOS applications or DAOS containers, which would be a run or an application's data, would sit in that namespace and look as if it was a bundle. So POSIX tools like LS or whatever would show just that container of data and not the billions of objects inside. And when the application ran, it would access the objects all in parallel through a different interface than POSIX. And another thing, since it's based upon a production file system, the tools, the administrative tools, and integration with HSM and other archives would come with this system because it's part of the same storage architecture that Lustre is based on. So it's a new I/O stack, parallel storage, the DAOS API on top of that, and then new middleware or middleware to use, modified to use the DAOS API on top of that. Supports tens of billions of objects. In theory, it's going to be completely parallel. Thank you.
Good afternoon, everyone. My name is Christopher Mitchell. I'm from Los Alamos National Laboratory, and just want to take a couple minutes to go over some of the work we're doing for visualization and analysis at scale. So coming from the high-performance computing realm, we are starting to get inundated with large data. As was said earlier, HPC users are trying to simulate the world and the products we use within it. And so if you take a cross-section of what we run on our clusters, you'll typically see stuff along the lines of climate simulations, high-energy physics, defense problems, etc. And it's not unheard of for these simulations to be detailed enough to produce terabytes, if not petabytes of data for every run. And what we find is that obviously raw data is useless unless you analyze or visualize it. So what we've turned to is a tool called ParaView. It's a scalable open source platform that's tailored to the high-performance computing environment. And it works using data parallelism. So that lines up nicely with the large volumes of data we're getting. Also, as a byproduct of that, we get data streaming, so we can incrementally process through what's requested, and we can do multi-resolution work where we can scroll through results immediately, but we get a summary view, and then the fuller resolution pictures come in over time. So just putting an example up on the screen real quick. This is one of our plasma simulations. This is looking at magnetic reconnection in particular. For this particular run, one vector field worth of data for one time step totals out to 6.9 gigabytes of data. Now, in a typical simulation run, it's not unheard of to have hundreds to thousands of time steps running, multiple vector fields being saved, and a couple of scalar fields for good measure. And so as you can see, the amount of data that we're saving out from one simulation run adds up very quickly. So what we've had to do is initiate a project to rethink how we do I/O and pair review to handle this problem. So as has been talked about, our current situation is we use a parallel file system to access the data over a storage area network. This is becoming more and more expensive to bring the data to the processor, and the side effect of that is that the user applications no longer are interactive. And so what we've done is we've said, okay, well, let's take the pair review I/O system, let's rewrite it so that it uses the Hadoop distributed file system instead of a parallel file system, and we're going to go ahead and process the data in situ to where the data lies. Now, the trick to this is PairView is not a MapReduce application. It's an MPI program. So what we had to do is devise a scheduling algorithm that would place these MPI processes on the data nodes that actually were storing the chunks we needed to access. And ultimately, we want the goal of no network transfers. And so when we actually implemented this, what we found is we got approximately a 3x improvement in read time compared to existing solutions. And so what used to take about 1.5 seconds to load per time step now started coming in at about half a second to load. Now we can start playing around with interactivity again. And as another nice byproduct of this, we started getting a more consistent standard deviation on the results, meaning that we're getting consistent read times instead of large fluctuations in how long it would take to bring in data. The graph you see on the side shows the results plotted out when it was run on 128 nodes of one of our test clusters. The light blue line all the way on the left-hand side from your perspective shows the read time coming off of Lustre. And then we see that the read times on average progress downwards when we migrate over to using HDFS, followed by the two different revisions of our I/O system that encompass the scheduling algorithm within it. So this is basically where we stand right now. If anyone wants to play around with PairView, it's available at pairview.org. And within the very near future, we'll be pushing this HDFS plugin out to open source if possible. So thank you.
Jane Mandelbaum from the Library of Congress. I'm going to talk about some practical solutions that we're currently doing in the area of digital preservation of the data, whether it's in a database, whether it's not in a database, we don't really care. Okay, so the library has sponsored a major digital preservation initiative called the National Digital Information Infrastructure and Preservation Program, and we have a website, digitalpreservation.gov, that's got a lot of useful information on it. We're also starting a new initiative called the National Digital Stewardship Archive. Alliance. And that initiative, we're encouraging members from any kind of organization, commercial, non-commercial organizations, to join us. All we ask is that you have a commitment to the preservation of content and that you join some of our working groups. So if you're interested, go to the website or come see me afterwards. So we may not have big data all the time, but we have biggish ideas. We know that it's really important to involve everybody in digital preservation. It's not just about one organization, so it's a distributed collection, and it requires a distributed infrastructure. And one of the other things that we're doing that we try to change the mindset of some of the people in our community is not to treat metadata records as records, but to treat them as data. So for example, traditionally the Library of Congress, we think about catalog cards, and we're trying to make people instead think about linked data. This is a visualization actually of the Library of Congress subject headings that we worked on actually with some computer scientists here at Stanford, and that's showing all the subject headings as sort of linked data. So what we're doing now is we have a new platform that we're working on with some of our partners called Recollection, which is for generating, customizing views. It's a kind of visualization. And it's not as cool as some of the other pretty spectacular visualizations we've seen here, but it serves sort of a different purpose. So what it does is takes your typical sort of, this is XML, metadata records. Here's your spreadsheet of some more metadata records. And it turns it into something that looks like this. So as I said, this is a result, and you can see it has different kinds of visualizations. You can pick a map, subject facets, and search. And it's not new tools. It's built out of existing tools. So why does this matter? It's because it's useful for the people we work with often to use this to create their data. They ingest it, augment it, they can design their own views, they can publish and embed it, and then they can share that data. So this shows how you can do that in the product. You can pick your own views, and you end up with something like this. One of the other things we try to have people focus on is saying, you know what, it's not just about the metadata records, but pointing to the data behind it to try to get users interested and know that there's data behind it. And one of the reasons we care about that is because everyone knows that preservation is not going to happen without either current access or the promise of future access. And unless you know what's in there, and unless you can tell your users what's in there, the data is not going to get preserved, and it's going to eventually disappear. So this is part of the goal of the project, is to try to encourage people who manage the content to look at the potential ways of turning their metadata records into views that might be of interest to other people so that people care about their content. So one of the things we also talk about is the importance of looking at the big picture. And here's your sort of typical map with the little bubbles. And maybe this is a good way of showing this. Maybe there are too many bubbles. You can take your data, you can iterate it, you can take a subset and put it back through the process. And one of the other things that we try to encourage people to do is, for example, Professor Holmes talked yesterday about statisticians who spend a lot of time fixing their data. Here, we actually try to encourage people to fix the data, to try to make it better. Here's an example of something that shows when the count of the facets shows up, one of them is misspelled. Tennessee is a hard word to spell, so it's not surprising. And we try to encourage people to fix their metadata and therefore fix the access to their data. So what we ask people to do is to look at the views and to try to also think about it as linked data. And not only to do that, but also share the data with other people. And this shows that you can, in fact, export some of the data from this tool. So what's next? We are going to have an open source release of this tool. And you can make it so it's both public views and private views within your community. We're going to be launching it as viewshare.org. We're hoping eventually to make bigger data sets available in the tool and using it as a portal and remix across data sets. So we now offer accounts on this system. And please explore joining the alliance with us. Thank you.
For more, please visit us at stanford.edu.